And now a man who needs no introduction. Oh, okay. Well, the person who you know is Dr. Rather, and others know as the mad scientist, and that's mad as in angry rather than anyhow. I just call him Dad. Uh, he has been an inspiration to me since before I was born. Uh, when he was 14 years old, he won the National Science Fair by building a planetarium, and 25 years later, I made third place, I think, in my regional. But hey, you know, it's an inspiration. He went to got his bachelor's here at the University of Tennessee and went to work at Oak Ridge National Lab. Then moved out to California to get his doctorate in astrophysics, during which time I was born. Then he became an astronomer, a radio astronomer, working at Kitt Peak, and one of the great thrills of my life was when he would take me up to the mountaintop for his observing runs, and I'd get to see how the big science works. But after a few years of that, he decided he couldn't support a family our size on the money that an astronomer makes, so he looked around to where the money is and saw that it was in the government and consulting, and so we moved on to Los Angeles and then to Washington, D.C. He worked at Command Aerospace, where he worked on the Star Lab, which, although it never actually flew on the shuttle, all of the but due to the Challenger accident, all of the proof of concept was done, and was a revolution in tracking. He then moved on to NASA, where, oh gosh, it's the, I don't know what his position was. Senior executive. It's all right, yeah. So he worked for NASA for a while, but then again, in this crowd, who didn't? We got one. Okay. Oh, sis, it's you. Okay. He then, because of the illness of a loved one, he left the government service and went to work for the Barbara Ann Karmanos Cancer Research Institute, where he put his knowledge of sensor technology to work, turning it inwards rather than outwards, and made several patents from that work that he did. After that, he has moved back to Oak Ridge and hooked up with all his old friends again and lots of new ones here at TVIW. And it is my great pleasure to introduce to you Dr. John Rather. Come on, Dad.
Well, he's the greatest son I ever had, and in fact the oldest one. And I've put up with a lot, obviously, but and I must mention another offspring who is sitting right back there. Gray Mays is my daughter, my oldest daughter, and a lot of what has happened this entire meeting is because of her. She is extremely well known in Washington, D.C., and in the Texas government spheres, and she's been with TI, Texas Instruments, for 23 years, essentially managing their connections with both Washington and Austin. And she has decided to retire at the end of this year and party for a while, and then heaven knows what she'll do next. But anyway, I'm extremely grateful to both of them for their help in making this a success, and it wouldn't have been a success without them, I'm sure. Okay, what I'm going to do is take a look at where things stand from yesterday and today. Numerous people have been saying, well, where's the synergy? And indeed, the pieces of the puzzle are all over everywhere. We've heard great talks, one after another, bringing up different viewpoints and different technologies and so forth. And I'm going to take a sort of different posture here and just sort of mix the puzzle around and show what might emerge from it. Some of the concepts go way back and some go forward into the future. I did go from here to working at Lawrence Livermore Lab back in the 70s, or the early 70s. And fortunately, I had a wonderful secretary named Lois Barber, who sympathized with me because in those days before computers, you couldn't get any illustrations done for your thesis, and you had to find an artist and then try to describe what you wanted. And since I always have liked pictures, I was getting nowhere. And she said, "John, just calm down." She said, "You're writing your thesis, and why use a picture when 1,000 words will do?" And so I'm turning the tables now with fond memories of Lois, and I'm going to sacrifice many words and just show you a lot of pictures to convey most of what I want to tell you about. First of all, just to put things in context, I think the things that we have looked at from the standpoint of this meeting are technologies and concepts and applications, systems planning, fiscal affordability, and timelines for doing things. And the technologies that we have examined in some depth, most of them are energy sources, nuclear, solar, beamed energy, and so on. Propulsion methods, again, nuclear, solar, and laser propulsion, and you're going to see some others. And superconductivity was mentioned in the surrogate talk for Jim Powell, who was the great inventor of superconducting maglev that led to the Japanese trains and many other things. And so I want to definitely show you some examples of what that can do. High energy lasers have been in my career way back. And 3D material processing, which we heard about from Bill Peter today. Von Neumann machines are machines that can replicate themselves. And of course, that idea goes way back to John von Neumann about 70 years ago. And then automated life support. We've heard a lot about the problems of life support, but Rick mentioned briefly my time 7 years working in cancer research, and I got very deeply involved in how to build automated detection of human pathology. I think this certainly applies to the future of everything we're trying to do, but I'm not going to explore that very much now. I just wanted to mention it in passing. The other side of synergy is the concepts underlying these things. You take the technologies and you put the puzzles together, and you can do things like capturing small near-Earth asteroids and in situ material processing, rapid commercialization, which is fundamental to make it pay for itself, and affordable development going into the future. I wanted to start, though, with an example of something that goes way back in terms of synergy. This couldn't be a better example, and of course it ties very closely to Phil Lubin's great talk yesterday, but I prepared this slide here for the director of the Livermore Lab just about exactly 30 years ago. We were trying to develop megawatt class free electron lasers and for ground to space based applications. And so there it was, and the Cold War ended, and we decided to instead beat our swords into plowshares. And so we realized early on that we could beam power to not a solar array, but a laser array of photovoltaic cells. And they are about 60 to 65% efficient because the band gap in the material is matched to the frequency of the light. And 1 micron is just fine, as Phil was talking about. So this means that a smaller collector, in principle, can capture light from a big transmitter on the Earth and can power directly the plasma engines here. Now, one of the big problems with Vasmir, for example, is that what kind of power supply is going to provide the prime mover for what you're doing. If you can beam the power to this thing, you don't need heavy stuff, because using silicon technology, you can have this pulsed coming up, and you can match the pulses to the impedance of the plasma device. And so, in other words, this is a tugboat which is powered from the Earth by transmitted laser power, and it can serve as a way of getting major payloads, maybe slowly, but from low Earth orbit to the moon, and you see it carrying quite a bit with it. On the moon itself, the same system, transmitting from 4 desert areas around the Earth, can lay down a spot on the moon from a 10-meter diameter transmitter that's about 80 meters in diameter on the moon, and everything is completely stable, because there's a beacon about 2.5 kilometers out there in the direction necessary because of the speed of light, that lays down the spot over here. The astronaut is showing you one of the laser cells, and here is the field full of them. You see here the assortment of things that the power can do at the megawatt level. It can run, it can charge the batteries on the bulldozer, and it can separate hydrogen and oxygen, which makes rocket fuel for this flivver up here that goes up and rendezvous with the tugboat coming in from the Earth. And you see the habitats covered over here by the bulldozer. And since Senator Hal Heflin from Alabama was our great mentor, if you had a high quality thing, you'd see right there one of those pink flamingos that you buy by the side of the road in Alabama. So anyway, that's ancient history. Now, we want to look instead at the principal topic that I want to go into is the capture of small near-Earth asteroids. And they will provide useful materials and radiation shielding, free rides from low Earth orbit to the moon, and I'll show you how it could even extend to Mars. On that subject, what I mean by a free ride, you may remember Apollo 13 that blew up and almost to the moon. And because it was in a free return orbit, it did a figure-8 loop around beyond the moon, further than any humans have been yet, 400,000 miles out, and they came back. Well, you can design things with the figure-8 orbits that dip just below the Van Allen belts and come near the moon or beyond it, and it continues to track that way indefinitely with very little change in velocity of the asteroid or whatever it is you put into that orbit. And so you can build a Trump hotel inside of it, and it will carry you up to the vicinity of the moon, and you can debark and go down and whatnot. Okay, now angular momentum pseudogravity. You heard a very good talk this afternoon, I guess, by Ken Roy, and you know what that's about. Impact prevention goes back to the threat of collision of asteroids or comets with the Earth, and solving the problem of harvesting these little 10-meter diameter asteroids solves that problem too. I'll tell you about it if I have time. Then we have interstellar launch, which I do want to get to at the end of this. One of my favorite pictures is this thing. It's a very old movie that was taken with 8mm stuff by somebody over the Jackson Hole area in the middle of a summer day. And you see up there coming across about a 10-meter diameter asteroid that grazed across the atmosphere about 40 miles up, and a couple of sonic booms and went back into space. But even then, in 1972, the Air Force had satellites looking down and measured the deceleration of it and was able to estimate the size. And the movie that went with it is here. You can see that it was in the sky for a couple of minutes, and everybody had a chance to see it. It turns out that one of these things, about the size of your house, passes through a sphere the size of the moon's orbit about once a week. And so it's good stuff, and if you can find the ones that have low relative velocity with respect to the Earth, you can sure use them. This is the first near-Earth asteroid that was discovered close to a century ago, Eros, and it's very interesting to look at that thing. You see there was an impact at fairly low velocity on this side that blew out a big plug on the other side and distorted the whole thing. And this is telling you that the whole thing is basically a rubble pile, and it just had enough gravity to hold itself together. But that is being borne out now by the Japanese mission that has a couple of little things hopping around on the surface of an asteroid and is going to bring back a sample to prove it. This was taken from 1 kilometer before the lander reached Eros, and you can see quite clearly what the surface is like. So if you're going to use the near-Earth asteroids, there are 3 essentials. You got to find them and get to them and tame them. And as has been shown several times in this meeting, the main asteroid belt is what people normally think about, and we're in here, the blue orbit there, which looks pretty empty, but it isn't. There are probably about 1 million of these asteroids the size of your house there that are available. More than that, it's been well known for well over a century that Jupiter is here with its family of stuff, but around here and around there are what are called the Trojan asteroids in the L4 and L5 points on the Jupiter orbit, and we can expect to find similar ones on the Earth orbit that are available at very low velocity. If you don't know, I imagine everybody knows by now about the Lagrange points dating back 250 years or so. But this is with the Sun and the Earth, and L4 and L5 are 1 AU. This is 1 AU and 1 AU this way, and that way you have these regions where things want to be trapped and are easy to get at. And exactly the same thing pertains around the moon, the moon's orbit around the Earth. You have an L4 and L5 region on that, which is a nice place to park things if you want to work on them. Detection is best done with satellite out at L2 between the Earth and the Sun, looking back in this direction with a wide angle and using infrared. And that can hand off to radar, which being inverse force power, it's hard to search the whole sky with radar, but if you can get on it, you can do quite a bit. And this is an example here. This is a radar image taken by JPL from the Goldstone site over a period of about 8 hours. And you see this little thing is rotating around 2 axes of rotation, and it looks a lot like a lot of other things. Okay, so we want to attract some method of getting dust and usable materials from these things. And only 60 centimeters or so, of 2 feet of dust surrounding a habitat with humans inside provides as much shielding from radiation from solar flares and cosmic rays as our atmosphere and magnetosphere above us right here. So it's a simple thing to solve if you've got the materials. Now this is where it gets fun, because we're going to use magnetically inflated cable in a variety of ways that go beyond a lot of things that have been talked about. But the fundamental experiment was done by Ampere himself in 1835, and anyone who's had a little bit of electrical engineering knows that the right-hand rule that if the current's flowing this way, the magnetic field goes this way. So if you have a long wire that goes up and turns around and comes back with a battery at the bottom, the current flows like that, and the field's opposed, and so it wants to jump out and become a circle like that. And it turns out if you do this with high temperature superconductors, that you can get very high currents flowing in that ring, and it can do beautiful things. So let's explore that. I published this paper with Jim Powell 10 or 15 years ago. Okay, now what we're looking at here is a 1 kilometer diameter, 1 kilometer diameter membrane that's stretched across. The currents are flowing here and this, and you're looking at it edge on. Down here is the Hubble Space Telescope, the James Webb, the Keck in Hawaii, and the Magellans that are now being built. This is 30 meters, and this is 1 kilometer in diameter. And this is the easy way to build kilometer diameter things. The fibers are stretched across. You have the thin membrane here. But not only is this an imaging telescope, but it has to be a player in the laser beaming thing. It gets you into 1 kilometer diameter laser projector territory. What's much easier to do than that is to have 3 conductors, one here, and one up here. And when you start the supercurrent flowing, it makes you a 100-meter diameter solar concentrator that the 100-meter diameter solar concentrator can deliver 10 megawatts at the focus. That's a lot of power. So I'm going to show you now how to capture that. This is a payload that will fit in the Falcon 9. And the supercurrent, it's been supercooled by liquid nitrogen before launch. And the current is from a battery to start the supercurrent flowing. And so it deploys and stretches out and forms that huge reflector, 100 meters in diameter. In this room somewhere is a very nice person named Chan-Chi Huang, and he is an old friend that we've worked together for 20 years, but his wife is one of the leading authorities in the world on coatings of various things, and she assures me that this can have a polymer coating on the back that we turn it to the sun, and ultraviolet will make it rigid so that once it's deployed, it's permanent essentially. The thing you can do with it now is apparent. It has that ring inside of the focus. It's pretty hot, but it has enough propellant in there to maneuver with and to irradiate the asteroid. And basically you're turning this 10-meter diameter asteroid into a little rocket. And if you do it, you remember the tumbling one that I showed you, if you do it right, you can get it in barbecue mode so that you trim the asymmetries and make it possible. And okay, did it get to the thing with this propulsion system? Probably not. It used a particle bed reactor to deliver it real quick so that it could rendezvous with the asteroid and then do its job. It turns out that in if the delta V required is only 1 kilometer per second, then you can trap it into the L4 and L5 orbit around on the lunar orbit in just under 5 days. If it's 5 kilometers per second, it takes 2 weeks or a little more. But it's entirely doable, and the amount of mass that's remaining in the thing after you've evaporated away to make it a rocket, in this case it's close to 1 million kilograms, and in the worst case it's down around 250,000 kilograms. Still an awful lot of useful material, you see. Okay, now this is kind of fun. Looking at how do you deal with this, how are you going to industrialize it? You have your nuclear particle bed reactor here that is driving the service system that is going to make use of it. And this is viewed from from the side. By the way, the same reactor here is also going to power this apparatus that's out in front. Now we're looking at it from the front side. And it's approaching our captured asteroid, which is there. And so you follow what's happening. It extended out, and now it's coming together. And you notice that you have the drilling rigs on both sides. And I should have, I'll back up just a little bit and show you that there are tubes capturing the gases, and the materials can be conveyed out, so you collect the dust and so forth as well. Okay. The next thing you can do This gives you the means of recovering, as you see, 500,000 kilograms of material on average. And you can think of what Bigelow has done already, the inflatable habitat that's now coupled to the space station. If you think of two inflatables inside of each other with a gap between them, you take the asteroid dust and fill it up. And so now you've got the shielded container that people can be very comfortable inside in a place about the size of your house. This is how we're going to solve the gravity problem between the Earth and Mars, and that is we've captured and engineered two of these asteroids, and they're there and there, about 0.5 kilometer apart. And so the way it works is that they're connected together by carbon filaments, and you cause the whole thing to spin in the usual way to provide centrifugal force, and there in the middle is the lander and its docking chamber, and you have the hollow tubes so the astronauts can travel back and forth. Maybe the farm is in one of them and the habitat in the other, but you see that it it's very feasible, and if we really tame these things, we can build a lot of them and make them routinely available once every couple of months to get on board. And you might take a year to get there, but it would be, you would play computer games all the way. I'm going to skip this because it's easy to say that having solved this problem, it also solves the problem of the threat of impact from asteroids and comets. I chaired the first study of that at Los Alamos in 1992 and reported it out to Congress. And the point is that you can put these in the incoming path out 1 million kilometers or more from the Earth, have several of them there, and where you know that gravity is going to bring the thing in. If it collides with this, then you get a nuclear class explosion. I won't get into the details, but if the relative velocity happened to be 40 kilometers per second, then it's equivalent to 75 kilotons of energy released in the collision with one 10-meter diameter object. Okay, then how do we industrialize them and to implement all these nice things? I think that the real ace in the hole is von Neumann engineering, and that's these machines that can replicate themselves. And it's a step beyond robotics in the usual sense. All the 3D printing stuff that Bill Peter was talking about applies, but it's possible to have hierarchical synergy so that tiny machines can beget giant projects. Micro to macro von Neumann machines can be developed initially to colonize our solar system, and I can show you that they can evolve to technologies for interstellar travel. The micro technologies are very near the present state of the art. Microelectromechanical systems, MEMS, are everywhere already, and three-dimensional printers, those two are very synergistic. So we need to generate tiny first-generation devices that progressively build larger next-generation machines, both individually and collectively. At that, we want to start parallel development of those. It's perfect for academic scale stuff, and I think that can be moved very fast from where it is now. Then hierarchical synergy is very powerful because these tiny machines can beget giant projects, and they can be developed initially to colonize the solar system and then evolve to the interstellar stuff. So how do we progress to interstellar launch? And this is something new that hasn't been mentioned at this meeting. I called ultralight interstellar probes 1 kilogram, not 1 gram, and we were looking for ways of doing that. And Jim Powell and John Mankins came up with an idea that we call star sling. Now, someone said earlier today that the enormous amount of energy to do anything is always with us. If you went straight ahead with your laser beaming, 10 to the 14th joules, or 100,000 gigawatt seconds, would be, with 50% efficiency, would be required to get this thing up to 3% of the speed of light. The total generating capacity of the United States is 1,100 gigawatts, so it could launch 1 kilogram in 100 seconds if we stopped everything else. But the 100-meter diameter solar concentrator in space provides 10 to the 12th joules per day. So if you can figure a way to do it over a period of 200 days, then it can launch that 1 kilogram. And so how to do that? Well, it's well known that this superconducting ring at CERN discovered the Higgs boson. It has 1,600 magnets that accelerate protons to light speed, and after going 11,000 orbits around there in 1 second, you're traveling at nearly the speed of light. So people say, well, why don't you just do this to accelerate something to the stars? And the answer is it takes a heck of a lot of protons to make 1 kilogram, and more than 10 to the 23rd. And so what turns out, though, you think about race cars. If you want to go from 0 to 200 miles an hour straight on, you need 1,000 horsepower. But if you will settle for 2 horsepower, you can just go around and around the track for a while, and you build up speed gradually. And it's the same principle here. This is called star sling. You've learned how to industrialize the small asteroids, and you've strung them out all the way around the Earth or some other planet. Around the moon would be fine. Far enough out so that the centrifugal force is just right. It's not going to it's going to be transferred to the tension in this cable here. And the maglev device that's riding on this, the only superconductivity is in that device, and the current in the coil there is what's driving it. And you see what happens. This picture was taken in about a millionth of a second, and you can see that it has been hurled off to Alpha Centauri. So this is a different approach that gets you up to 3% of the speed of light, and that would get you there in 160 years, including deceleration. And so the membranes stretched by Mc solve a lot of major problems, and the kilogram payload seems to have a lot of ability that's possible. And so we can imagine being able to deliver to planets around nearby stars the receiver for stuff like this. We build creches and AI nannies in these places, and then we send the final payload, which weighs 400 micrograms, and we land that on the planet. Fortunately, every woman knows how to manufacture one of these once a month. It's an ultimate example of a Oracle von Neumann machine, and you put it in the right environment, and 9 months later you get a beautiful baby, and 15 years later you get a teenager, and that's your problem to deal with.